In this lecture, we are going to discuss about Liouville's theorem. First is definition of the integral function. Integral function. Integral function. If fz is analytic for every finite region, in the z plane, then fz is called integral function or entire function. Next is statement of the Liouville theorems. Statement of Liouville's theorem. If fz is integral function satisfying the inequality for all values of z and m is positive constant, then the function fz is constant. That is, if fz is analytic at every point of the z plane and satisfying this inequality, that means fz is bounded, fz is analytic at every point of the complex plane, z plane, and fz is bounded, then my function fz is constant. That is, if we show that for two different value of z, their functional value is equal, then we are done. This theorem equivalently stated as, in other words, a bounded entire function is constant. Proof. Suppose z1 and z2 are any two points in the z plane with z1 as center and radius r as radius, we draw a circle gamma whose equation is z minus z1 is equal to r take are sufficiently large, take are sufficiently large so that Z2 lies inside gamma and mode of Z1 minus Z2 is less than R by 2. If we draw the figure, we will see this one. This is my circle. Suppose this is the center of the circle. This is Z1. This is the radius R, and this is the circle. Z2 is any point, and distance between Z1 and Z2 is less than R by 2. Since fz is integral function, so fz is analytic at every point of the z plane. That means fz is analytic in the circle gamma. So by cos and z1 and z2 are any two point inside gamma. So by Cauchy integral formula, Cauchy integral formula f of z1 is equal to integral 1 by 2 pi I 1 by 2 pi I 1 by 2 pi I integral gamma over gamma f of dz z minus z1 fz dz. That is fz1 is given by 1 by 2 pi I integral over gamma fz dz by z minus z1. Similarly, fz2 is given by this integral gamma fz z minus z2 dz. Now to prove the given theorem, we have to prove that f of z1 is equal to f of z2. For that, we will consider f of z1 minus f of z2. F of z1 therefore minus f of z2. This is equal to 1 by 2 pi I integral gamma fz dz z minus z1 minus 1 by 2 pi I integral gamma fz dz z minus z2. Now take common 1 by 2 pi I by 2 pi I integral gamma and fz. Within bracket it is 1 by z minus z1 minus 1 by z minus z2. Bracket close, this is dz. So this is equal to, if you simplify this one, you will get this z minus z2 minus of z minus z1. That is minus z plus z1. Here it will be z minus z2. Z cancel out. Plus z minus z will cancel out. I will left with z1 minus z2, as here minus plus. Here it is minus. So it is z1 minus z2. Since our differentiation is with respect to dz, so that can be taken out. Z1 minus z2 by 2 pi I integral gamma fz z minus z1 z minus z2 dz. Now take modulus on both sides. Before that, you should put this equation 1. Then, since equation of the circle is this one, now find out this value z minus z1 I'm adding and subtracting the same quantity. This will remain as it is. In the next, I will make some rearrangement, that is z minus z1. Take minus common, it will be z2 minus z1. This, by using the properties of modulus, I will get this one. This is z1 minus z2. Okay. So this is z minus z1 minus z2 by z1. Okay. Rub this out. This is my r. This is equal to r, and this portion is my less than r. Okay. So this portion will be my, as this portion is less than r, so if I minus this less than r portion, that is this, initially I have assumed this is less than r, so this must be greater than r by 2. This difference must be greater than r by 2. Okay. And modulus fz is less than equal to m, it is given. Therefore, taking 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 modulus on both side of this equation 1, both side of 1, we get modulus fz1 minus fz2 is equal to modulus 1 by 2 pi I z integral comma fz z minus z1 z minus z2, this is dz. This is modulus. So using the properties of modulus, z2 minus z1 by 2 pi, since I can be written as 0 plus I, so modulus of I will be my 1 square, that is 1. Okay, here coefficient is 1. So then this will be integral comma mod of fz, mod of dz, and mod of z minus z1, mod of z minus z2. Since this is my m, this is m, this is m, it is given, this is m, it is given. So this can be taken outside the integral sign, that is this is z2 minus z1 divided by 2 pi, it is m, and here it is z minus z1 is the equation of the circle, it is r, and z minus z2 is this one. We have subtracted a quantity which is less than r, that means from r I am subtracting a quantity which is less than r, so this quantity will be greater than equal to r by 2. So substitute this value, this r, then integral comma dz. Okay, as this value are r, which is independent of dz, So this can be taken outside the integral sign, and this cancel out. This will be my z2 minus z1 m by pi integral gamma dz. In the lecture of example on complex integral, we have find this one. This is one is the length of arc. Here arc is my circle, so that means length of arc is the perimeter of the circle, and perimeter of the circle is 2 pi r. So put that value. This is equal to z2 z1 minus z2. Even if you write z2 minus z1, that is also correct. M divided by pi r squared, or pi r squared. Here it is r squared, divided by pi r squared. Here it is 2 pi r. Since integral comma dz, mode of dz is 2 pi r. 2 pi r. So r cancel out, pi cancel out, pi cancel out. This is less than equal to. That means modulus of fz1 minus fz2 is less than equal to 2m z1 minus z2 modulus divided by r, which tends to 0 as r tends to infinity. This implies mode of z1 minus z2 is equal to 0. This implies f of z1 is equal to f of z2. When f of z1 is equal to f of z2, this implies two functional value are same. That means fz is constant function. Fz is constant. Hence the theorem. With that, I would like to conclude. Remaining will be in the next lecture. Thank you.